Okay, here we go again. Chemistry 3202, course overview review, Unit 2, Section 2, Lesson 2, pH and pOH calculations. These calculations I always dealt with, always a couple multiple choice on the exam, just testing whether or not you can use your calculator and whether or not you can calculate the pH and pOH given different values. So let's have a quick look at this. This is dealt with on page 567 to 574 of your textbook, and there are a whole bunch of questions in your book that relate to this material. And of course on page 574 these answers are provided in the back of your book. So good ones to try to see if you can do the calculations. Here are the outcomes for this lesson. When we talk about the pH, we refer to a pH scale. Now many people are already aware of what a pH scale is. It's a pH scale that generally ranges from 0 to 14. However, we can be outside the range. We can get negative pHs, we can get pHs that are up around 15, 16, etc. But generally for the concentrations and materials that we use on an everyday basis, I guess in the lab, and common everyday household items generally fall within the range of 0 to 14. All right, but be aware that the pH scale can range outside 0 and 14. It can be negative, it can be larger than 14. So what is this pH scale? Now this pH scale is based on measurements of 10. It's powers of 10. And what happens here, of course, you've been noticing in the last lesson when we were doing the KW calculations, we were getting lots of nasty little exponents, 10 to the minus 14, 10 to the minus 12. Very inconvenient numbers. The numbers really, you really have to think about what the number represents to get the meaning from that number. So what we want to be able to do here is kind of simplify what these numbers are representing and what they're showing us. So what we're looking at is the idea that the pH scale expresses the acid concentrations in terms of base 10. So everything is counting by tens. And we want to try and simplify it in that sense. So we have two calculations that we're going to look at here. We have the first calculation, pH equals minus log base 10 of the hydronium concentration. And if we take the reverse of this, if I'm going to give you a pH, I can say it's the second function or inverse log, and that's 10 to the minus pH, and that'll give me H3O+. So we have two ways of calculating. First, I'm going to give you H3O+. We can calculate pH. In the other session, on the other formula right here, I'm going to give you the pH so that you can find H3O+. So let's have a quick look at some of these calculations. Okay, in this particular example, we're saying, what is the pH of a soft drink like Coke or Pepsi or orange or root beer? And we've measured it to find out that the hydronium, the H3O+ concentration, is 4.5 times 10 to the minus 4. Well, what we're going to do here is simply take this concentration and put it in our log formula up here to get the pH. So here we go. So when we do this calculation, you want to put this in your calculator, and there's two ways we can do it, and again, I'll show you how. It's the log button on your calculator, and you're going to have to put in 4.5 exponent negative 4, or if you're using the times 10 business, you're going to press log bracket 4.5 times 10 exponent negative 4, and you should get this number showing up on your calculator. Now this negative sign is removed by putting in the negative log. So if I put the negative log in front of these two, then the negative sign would be removed. Okay, so our final answer would be pH equals minus log of H3O+, so it's the minus log of 5.45 times 10 to the minus 4, and the negative will cancel out here, so we get a positive value for pH. Now this value, 3.35, we can estimate what this value is going to be, because whatever this exponent is right here, the pH is going to be somewhere between 3 and 4. So it's going to be between 1 less than that exponent. If this was a negative 6, then my pH would end up being between 5 and 6. If this was a negative 10, then my pH would end up being between 9 and 10. So because this exponent is negative 4, my pH, I'm estimating it to be between 3 and 4, and lo and behold, when I calculate it, there you go. So I know if I'm on the right track. I know if the answer that's coming out of my calculator is in the right vicinity, because I expected it to be between 3 and 4. Lo and behold, it is. Let's just try this calculation on our calculator. Now I know if you guys are viewing this through the MP4 file, you won't see me share the calculator, but if you're viewing it through the jar file, then you can see what I'm doing. Okay, that's 4.5 times 10 to the minus 4. So let's have a look at this and see what the calculator is going to look like. So here we go. We turn our calculator on, and what we have to do is we have to use this log button right here. So I'm going to put in minus log, and you notice how the bracket comes up automatically. 4.5 times 10 to the power negative 4. Close your bracket and hit enter. And there we go. 3.347 is my pH. Now if I wanted to do it the other way, okay, if you like doing it with the exponent feature, you can go minus log 4.5, second function, see the EE, exponent, negative 4. And we get the same answer because, of course, it's the same thing. So that exponent is the same thing as saying 10 to the power. There we go. So that's how we get that answer. All right, very important that you know how to use your calculator. Here's another couple calculations. In this case, we have an acid being given to you. In part A, we're saying we got 0.494 moles per liter of nitric acid. And we're looking at this now. It's going to be very important whether this is a strong acid or a weak acid, isn't it? So when we look at this guy, we're saying, hey, look at this. Nitric acid, you check your tables. It's a strong acid. So we know that it's 100% ionized. We know the concentration of nitric acid. It's 4.97 times 10 to the minus 1, or you can leave it as 0.497. It's a strong acid, so the concentration, it's a 1-to-1 ratio. If this was a weak acid, then you'd have to do the percent reaction calculation, wouldn't you? We did that in the last lesson. In this case, it's a strong acid, so we simply use the concentration as it is. And when you plug this in your calculator, minus log of 0.497, and again, the reason I changed this to scientific notation was to say, okay, I want to estimate my answer. It's going to be somewhere between 0 and 1. And lo and behold, there it is. The answer is 0.3. So it's not a mistake. The pH can definitely be a decimal. The pH can be a negative number. The pH could be greater than 14. But in this case, we estimated it to be between 0 and 1 because that's the exponent there. And lo and behold, that's the pH. Fairly acidic. It's a strong acid. Okay, here's another example. 1.3 times 10 to the minus 2 moles per liter of hydrobromic acid. And this is also a strong acid, so the concentration of H3O plus is the same thing here. Now I'm going to estimate this guy. It's got an exponent of minus 2, so I'm predicting the pH should land somewhere between 1 and 2. All right, let's do the calculation. And lo and behold, we know that the concentration of H3O plus is equal to HBr because it's a strong acid. pH minus log of the H3O plus, there we go. We plug in our values, and look, we predicted it to be between 1 and 2. There it is, 1.9. Okay. Okay, we want to look at this and say, okay, how do we do this in reverse? What if I give you the pH? If I give you the pH, I want you guys to figure out what the hydronium ion concentration is. So what this is on your calculator is the inverse of log, or the second function of log. So on your calculator, the log button up above it, it has 10 to the x. In order to get access to this, you have to press the shift button on your calculator and then the log button, because 10 to the x is going to be 10 to the minus pH. So let's look at an example. All right, we're looking at this particular one here, and we're saying a sample of vinegar has a pH of 2.89. We want to calculate the hydronium ion concentration, and we're saying that the pH is 2.89, so I go shift log negative 2.89. And a lot of people forget to put the negative sign in here, and as a result, they end up getting an incorrect answer. But don't forget the negative, or if you're doing this, shift log 10 to the power negative 2.89. And of course, you punch this in your calculator, and lo and behold, don't forget the negative sign, and we get 1.288 times 10 to the minus 3. Now, could I predict that that value was going to be to the power minus 3? Absolutely, because the pH is 2.89, right? This is 10 to the power negative 2.89. So it's going to be somewhere around negative 3. So I should be able to figure out and estimate my answers. Okay, another example here. It's saying, what's the hydronium ion concentration of a sample of blood with a pH of 7.4? Okay, well, again, it's going to be pH of 7.4. So I simply plug these values in my calculator. Second function log negative pH of negative 7.4. Let's try that one. All right, this one has a pH of negative 7.4. I'll share my calculator with you again. If you're looking at this, of course, on your jar file, then no problem, you can see it. So here we go. We want to turn on my calculator, and I'll clear it. And I'm simply going to go Shift, log, and don't forget the negative sign, negative 7.4. Close my brackets. I made a mistake. Negative 7.4. There we go. That's better. And enter. Okay, 3.981 times 10. That's what the E stands for, times 10, remember. So 3.981 times 10 to the minus 8. Somewhere around where it should be because the power is 10 to the minus 7.4. There we go. Okay, so 3.98 times 10 to the minus 8. And it's moles per liter because it's a concentration, square brackets. There we go. Okay, we're looking at this and we're saying, okay, let's look at some common things that we see. And remember, we said common things around our household generally fall within the range of 0 to 4. So we can look at, say, cola like Pepsi or Coke or some other brand of cola. Acid rain is pH 10 to the minus 4 or pH 4. Okay, ammonia window cleaner, pH 11. All right, very basic. Drain cleaner, there we go. All right, so common everyday things. You wouldn't deal with anything other than battery acid at the low end. That's as acidic as you generally would deal with, or drain cleaner at the other extreme here. But again, be aware that you can have negative. You notice how this arrow is pointing. It keeps going in both directions. You can have a positive 15 for a pH, and you can have a negative 1 or a negative 2. It just depends on how concentrated and how strong the acid or base is going to be. So don't be, if you see that on the public exam, if it works out to be a negative pH, that's possible. That would be a very concentrated, strong acid. And if it was a pH of 15 or 16, that would tell me it was a very concentrated, strong base. Okay, so be aware that you can get them outside the range. What's the significance of the pH scale? Well, we said the pH scale is a log scale. It's counting by factors of 10. So if we look at this on the bottom here, we're saying, all right, we're going up by 10s each time. So a pH of 0, a concentration of 10 to the of 1 would have a pH of 1. If I go up 10 times, then the pH goes up by a factor of 1. So with one change in pH unit, because remember pH is going to be a log base 10, we're increasing by 1 pH unit, and that's representing a 10 times change in the concentration. And if we go up another pH unit, then that's times 10 times 10. So you look here, we've gone up times 10 and times 10. But if we skipped 2 units, if we went from 0 to 2, then we would go times 10 times 10, which would be 100 times larger. So if I skipped it and went 2 pH units, that would be times 100, because 10 times 10. If I skipped to 3, if I went from 0 to 3, that would be 10 times 10 is 100, times 10 is 1,000. So what we're looking at here is every time we go up by 1 pH unit, it represents a 10 times change in the hydronium ion concentration. If I go up 2 pH units, then it's representing 10 times 10 or 100 times change. And if I go up by 3 pH units, it's going to be 10 times 10 times 10, which is 1,000 times change in the hydronium concentration. So what's so significant about that? Well, a very, very small change in pH represents a significant change in the overall acidity, because it's the concentration of H3O+ that gives the acid its its acidic properties, whether or not it's going to turn blue litmus red, how reactive it's going to be with metals to produce gas, right? So the bigger or the stronger the acid, the more the H3O+, the faster the reaction is going to be. So this is very, very important. So the concentration of hydronium is what leads to its desire to want to be an acid. So the pH unit is simply a way of simplifying these numbers. So a very, very small change in pH, even though it's saying a pH of 2 units, that's a very significant change in that test tube, because a change of pH unit, 2 pH units, is representing 100 times change in the concentration of H3O+. Let's look at an environmental concern here, or an environmental aspect of this, and we're saying, okay, we got this little goldfish floating around in his closed container. He's only got a little tiny bowl to swim around in. In that bowl, we're sprinkling food. The food eventually decays. Anytime protein and whatnot decays, it produces acidic byproducts. The little goldfish is also defecating in its environment, all right? So the goldfish poop is decaying and producing acidic byproducts as well. So what happens is, over time, this goldfish container is going to start to become more and more acidic. So if we looked at this goldfish and we said, as soon as we put the water in, it's nice and fresh, right? They're on a pH 7, nice clean water. If we, after say 2 or 3 weeks, go and do another measurement of the water in this tank, and it ends up being pH 5, we can say, big deal. The pH is only changed by 2 units. Not very significant, or you might think. But now you know what the pH represents. We're saying, hold on now. This pH change from 7 down to 6 down to 5, that's representing 10 times 10. That's 100 times more acidic than it started out to be. Let's take you and put you in an environment where your oxygen is 100 times less than what it is now. See how well you cope. So you've got your little goldfish here in a container that's 100 times more acidic now than what he started out to be. That goldfish is probably not going to survive. That's a very drastic change in its environment. So the goldfish's environment is now 100 times more acidic than it started at. It's probably going to get sick and die. All right? So when we look at this from an environmental concern, you might say, well, regular rainwater is pH 6. Okay, good. Acid rain is pH 4. Yeah, that's only 2 units. Hold on, back it up. 2 units, that's 100 times more acidic. Very, very serious, very significant to the environment. Biological systems, although they can adapt somewhat, they have a very difficult job of trying to adapt to very significant changes in their environment. So there we go. Sometimes you see that type of question come up on the public exam, right? They'll ask you, a pool changes from pH 6 to pH 4. Is that very important? The answer is definitely, right? It's 100 times change in the acidity. There we go. Okay, same thing works in the other direction. If we went from pH 5 to pH 7, then we would go the other way and it would become 100 times more basic. And that would be serious too, depending on the condition and what we're looking at. Okay, we also now want to do a comparison of H3O plus with OH minus. So let's have a look at it. And here we go. If we look at the idea, now we've seen this graph a little bit before in the other lesson. We're saying, okay, in any given situation, if we have an acid in the solution, then the hydronium concentration is quite large, 10 to the minus 1. We also know that there's going to be a little OH minus present from the water. And what we're seeing is that it's very large if it's an acid. The H3O plus is very large. The OH minus is very tiny. And as we start getting more and more neutral, as we start moving more and more towards being neutral, what we're noticing is that H3O plus begins to balance out the OH minus. This guy would have an acidity of pH 1 because that's the hydronium concentration, pH 1. This guy here at pH 7, okay, it's becoming more and more neutral because now the H3O plus is equal to the OH minus, hence pH 7. That's representing the neutral pH. And as we start going to the other side here, we notice that the H3O plus is getting smaller and smaller and smaller. We're getting more and more basic. And you notice here, even though this number is very tiny, it represents a pH of 14, which now represents a basic solution. So as we can see here, H3O plus drops as we get more basic, but the OH minus is getting larger and larger and larger as we get more basic. Okay? So we can see that there's some kind of relationship here. This guy is 1, minus 1. This guy down here is minus 14, very tiny. Here they're equal. Here the H3O plus is very tiny, minus 14. This guy is large, minus 1. Okay, what's the significance of that? Well, if we can express things in terms of a pH, let's go back. pH is the log of this number, hence 1. pH log of this number, 7. pH log of this number is 14. So that's expressing the acidity in terms of pH, or hydronium. We could also turn this around now and express the acidity in terms of OH. I'll black this out or blue it out. If I wanted to take the log of this number, the log of this number now is going to be 14. The log of this number is 7. The log of this number is 1. So we could also, instead of doing pH, now we can do pOH, which is referring to acidity from the hydroxide perspective. So let's have a look at that. So acidity from the hydroxide perspective, it's the exact same thing as we've been doing, but this time we express it as pOH. So it's going to be the minus log of the OH concentration. Likewise, if I give you a pOH, you can get the hydroxide concentration. A real nice little relationship exists here. Everything is based on 0 to 14. So what we say is that the pH plus the pOH is equal to 14. So if I know one of these, if I know the pH, then I could easily get pOH by simply adding them together, and it equals 14. Okay, don't forget these calculations here, the kW for water. All right, if I wanted to calculate OH minus, it's going to be kW over H3O plus. And likewise, if I want to find H3O plus, I can find kW over OH minus. Let's try a couple calculations to straighten all this out. Here we go. In this particular calculation, we want to calculate the pOH of a 0.7 mole per liter potassium hydroxide solution. Okay, shouldn't be a problem. Potassium hydroxide is ionic. It's going to be 100% dissociated. So our concentration here is a 1-to-1 ratio. So the concentration of OH minus is equal to the KOH because it's 100% dissociated. And again, I put this in scientific notation to say, okay, my pOH should be somewhere between 0 and 1. All right, so pOH is minus log of OH. I simply plug it in my calculator, and there we go, to 0.155. That's what I predicted, between 0 and 1. Okay, here's another example. We want to calculate the pOH of some barium hydroxide solution. Now we got to watch this guy because barium hydroxide is ionic as well. It's going to be 100% dissociated, but look at this. It's producing twice as much hydroxide. So I'm going to have to do a little bit of stoichiometry here to figure out the hydroxide ion concentration. So we know that the hydroxide is going to be a 2-to-1 ratio of the barium hydroxide. So the concentration of OH minus is doubled. And now we can plug that in to get the pOH. Now again, I can estimate my answer. It's going to be somewhere between 2 and 3, 1 less than my exponent, right? So somewhere between 2 and 3. I plug this in, and there we go. I get a pOH of 2.30. Now what's the significance of this? I find it difficult myself to look at a pOH and be able to say if it's acidic or basic. So what I like to do is, remember this little scenario where we said pH plus pOH equals 14? What I'm going to do is I'm going to solve for pH here now and say 14 minus pOH. This ends up being a pH of 11.7, which means it's basic, because it's a pH above 7. So a pOH of 2.3 is a basic solution. It's going to have a pH of 11.7. So if you can't get your head around pOH, simply calculate the pOH and then change it into a pH, and that way you can easily say that acids below 7, bases above 7. There we go. And that would make sense anyways, of course, because this is producing hydroxide. Okay, here's another type of question that's saying, what's the hydroxide ion concentration of a solution that has a pH of 5.67? All right, now this is a pH, so this is based on the hydronium concentration, but I want to find OH. Okay, there's two methods that I can do here to do this. I can say, first of all, I can look at this and say, all right, I know the pH, so I can say something like pH plus pOH equals 14. So now I can solve for pOH. That's going to be 14 minus the pH. So that's going to be 14 minus 5.67. Okay, and what does that equal? Works out to be 8.33. And now that I have the pOH, I can easily get the hydroxide concentration because that's equal to 10 to the minus pOH. So you got to watch what they're referring to, whether or not they're referring to pH or pOH. So in this case, it's 10 to the minus 8.33. And what does that equal? Okay, it's 4 times 10 to the minus 9. There we go. Now that's one way we could do this. The other method we could choose to do this is I could say, all right, because I've got the pH of 5.67, I can simply get the H3O plus here now. That's going to be 10 to the minus pH, which is going to be 10 to the minus 5.67. Which equals 2.13 times 10 to the 2.137. Okay, that's moles per liter, and that's H3O plus. So I can look at that now, and I can go back to my last lesson and do the KW calculation, because we know KW is H3O plus times OH minus, and therefore now we can find OH minus, because it's going to be KW over the H3O plus. And we should get the same answer. Remember that KW is 1 times 10 to the minus 14 divided by 2.137. And what do we get? And again, I get 4 times 10 to the minus 9. And again, it's moles per liter because it's concentration. So two different ways of getting the answer, and of course the answers are all based on the method you choose are all based on this equation right here, the KW calculation. That's what this is based on up here. Assuming that for a neutral solution it's 10 to the minus 7, 10 to the minus 7, so 7 plus 7 is 14, right? So two ways of doing this. You can choose whichever way you want. I like doing it this way because the calculations are easier. A lot of people tend to mess up here, but just remember how to do this on your calculator and you'll be all right. So there we go. Okay, here's another calculation that we can do here. It says a properly calibrated pH meter shows a reading of 9.88. So that's pH, right? It's a pH meter, so it's showing pH of 9.88. We want to calculate pOH, H3O plus, and OH minus. Okay, so we're looking at this particular problem and we're saying, let's list down all the things we're given. We're given the pH, and here's the things in blue that we want to calculate, the pOH, OH, and H3O plus. Okay, now we look at this problem and we say, okay, well, it's easy to get pOH. Just subtract 14 from 9.88. pOH is 4.12. Okay, getting the OH and H3O plus, easy enough. We can get H3O plus by saying 10 to the minus pH. There we go. It works out to be 1.32 times 10 to the minus 10. All right. Now to get OH, there's two methods, just like we did on this other side. There's two methods. Method 1, now that we know the pH from up above here, we can simply do OH minus is 10 to the minus pOH. So we can plug that in, and lo and behold, we get 7.5 times 10 to the minus 5. You can check that on your calculator. Make sure you got the right answer. And the other way we can do this is, instead of using this value, we can say, okay, we've got H3O plus, let's do the Kw thing. So the other method to do this is to do the Kw thing. And there we go. So Kw is H3O plus times OH minus. Plug it in, get your values, and again, check your calculator to make sure you can get these answers. You can press pause at any time. Okay, here's another type of calculation. It says a window cleaning solution has a hydroxide ion concentration of 7.9 times 10 to the minus 4. Calculate the pH. Now you simply can't do the log of that because that's not hydronium, is it? That's hydroxide. So watch what they're giving you. That's the hydroxide ion concentration. You want to find pH. So what we have to do again is simply list down what we're given. We're given hydroxide. We want to find pH. Now, again, two methods. We could approach it from either direction. We could say, all right, now that we know the hydroxide ion concentrations, find the pOH. It's 3.102 for the pOH. I want to find pH. Simply subtract 14 here now, and you got your answer. Okay, that's an easy way. The other method, of course, is now that we have hydroxide, you can do your Kw calculation first to get hydronium. There we go. And again, press pause at any time to check these calculations. And now that we have the hydronium, we simply take the log of that to get the pH. And again, we should get the same answer. The way you choose to do it, it's up to you, whichever way you like to do it. Okay, but again, check the answers to make sure you can get these coming up on your calculator. Very important. Don't lose marks on your public exam because you don't know how to use your calculator. Okay, here's another important topic, I guess, that we deal with in this section, and this has got to do with dilutions. You know, what happens if we have an acid or a base and then we just dilute it? We add some water to it. So by diluting something, by definition of dilution, we're making it weaker. The concentration is becoming less. The acid or the base is going to be spread out into more water, and that's going to dilute it or make it weaker. So clearly, if we add water to an acid, we're making it weaker, which means the pH is going to start rising closer to 7. It's not going to be as acidic as it once was. Same thing with a base. If I add water to a base, it gets diluted, it gets weaker, the pH starts to drop closer to 7. All right, so let's have a look at it. In this particular question, we're taking 1 moles per liter of barium hydroxide. We got 25 mils of it, and we're going to take it to a final volume of 150 mils. Okay, so the very first thing we want to look at is I want to write down what I'm given and what I need to find. I've got an initial volume of 25 mils. I've got a final volume of 150. I've got an initial concentration of 1 mole per liter. I want to find my final concentration. So I'm going to do my CI VI equals CF VF business right here. Okay, solve for CF. This is 2202 stuff, remember? And there we go. Do I have to change my milliliters to liters? Not necessary, because they're going to cross out anyways. Okay, the final concentration of my barium hydroxide is 0.1667 moles per liter. It got weaker, didn't it? You know, initially we started off with 1 mole per liter. Now we've diluted it to 0.1667 moles per liter. It's a lot weaker. We want to calculate the pH of this. Well, it shouldn't be a problem. What you got to watch here, though, is barium hydroxide is a source of 2 mole of hydroxide. So whatever that concentration is there, now we have to double it because of our mole ratio right here. Okay, so our concentration now doubled because the barium hydroxide produces 2 moles of hydroxide. And now that we've got the hydroxide ion concentration, we can easily calculate the pOH minus log of the hydroxide. And now we want to get the pH. And again, there's two ways you could do this, but this is the way I chose to do it. And it ends up being pH equals 14 minus pOH. And works out to be 13.52. Aha, this is a basic solution. Okay, And that makes sense because it's barium hydroxide. It's producing a lot of OH. So there we go. Here's a few more problems you can try if you want. You can check these out with the free online tutor, or you can drop me a line if you want to try some of these. You can drop me a line and ask me to do a couple more if you like. But don't hesitate to use our online tutor and lots of the resources that we have online. Your textbook is good too. A lot of online resources there, and by all means check out the public exams and see what type of question they could ask you on this. Okay, bye for now.